Imagine. As Prometheus gave humanity fire, we are gifting the world cleaner homes. No longer the struggle of living in squalor and having your current robot vacuum needlessly going over clean spaces and knocking over precious family heirlooms. We are building a cleaning robot that maps out the layout of your room before planning the most efficient cleaning path, all while being able to detect and avoid new obstacles in real time. With a single press of a button, you'll be able to sit back and have a cleaner home in a faster and safer manner than the current vacuum robots on the market. The only thing we won't be sucking up is the money from your wallet. And as our model will remain competitive with other options available, all while delivering more. We knew coming in that the robot was going to be designed kind of like a Roomba, so kind of that basic outline or circle shape. But because we were using off-the-shelf components, we weren't really sure how that was all going to fit together. And so our first go-around for the robot design was really just kind of laser cut the general shape and then start hand drilling from there. So you kind of see it's a little bit like rough around the edges and everything, leading us into what would be our final CAD model of knowing where the parts were going to go. This process kind of helped teach us like knowing where to place the motors on the Roomba, knowing the placement and the weight balance between all the components, just because it's a very heavy battery in back, and balancing that out with the weight of the Arduino and Jetson. And so this was a really good step for us to make a full finished product in the end. Now let's take a look at the hardware that powers the MapSweep robot. Each component was carefully chosen to meet the demands of mapping, navigation, and cleaning functionality. The RP LiDAR A1M8 is our primary sensor for mapping and localization. We chose this 2D LiDAR for its affordability and reliability. With a scanning frequency of up to 10 Hz and a range of 12 meters, it provides sufficient precision for obstacle detection and mapping in indoor environments. Serving as the brains of our robot, the Jetson Or Nano was selected for its powerful GPU and AI capabilities. It's essential for running SLAM algorithms, path planning, and handling real-time LiDAR data processing. With up to 40 TOPS, or trillion operations per second, of AI performance, it handles computationally heavy tasks efficiently. The Arduino Uno handles low-level motor control. It receives commands from the Jetson via ROS2 and translates them into precise PWM signals for the motor drivers. This division of labor keeps the system efficient and responsive. We're using brushed DC motors with a torque rating of 1.275 Newton meters, which provides sufficient power to navigate various indoor surfaces, including carpets. These motors are optimized for smooth and precise movement, critical for obstacle avoidance and navigation. The robot is powered by a 12-volt, 5200 mAh lithium-ion battery. This capacity provides approximately 40 minutes of runtime under full load, balancing operational time and weight to meet our project requirements. We chose the L298N dual H-bridge motor drivers for their reliability and ease of integration with the Arduino. These drivers efficiently manage the power requirements of the motors and ensure stable performance during operation. Each of these components play a crucial role in ensuring the robot operates smoothly, efficiently, and meets the goals of precision and reliability for this project.
While we were in the process of building our robot, we built a simulation pipeline in parallel because we wanted to know how a robot would path and react to a variety of different room layouts and obstacles. The first step was building a robust random room generator. So for the purposes of navigation, we decided to model the room as an occupancy matrix, with ones as areas where the robot could traverse and zeros as areas that were blocked by obstacles. Then we added tunable parameters, allowing us to modify the room dimensions, the granularity of the occupancy matrix, the number of corners in the room, the type of obstacle, and even the rotation. So our next challenge was identifying the traversable spaces, the regions where the robot could and could not fit. Since our occupancy matrix could contain millions of points, and we want to be able to update the robot surroundings in real time, a simple sliding window approach was far too slow. So we had to come up with something different.
Our updated solution first applies a uniform filter to the entire floor plan the size of our robot, before doing binary dilation with a 3x3 struct element, which represents up and down, left and right, and diagonally. By adjusting the number of iterations on our binary dilation, we can also build in risk tolerances, allowing us to account for areas that the robot can't reach due to its turning radius. We're left with a high-fidelity room occupancy matrix that can be exported as a CSV or text file and used for path planning.
Now, after we completed the room simulation, we needed to design an algorithm for the robot to move around the room asynchronously. So our autonomous algorithm was broken down into two distinct phases. The first is mapping the room when the room was largely unknown. Then after that, we would load in our path planning algorithm so the robot could traverse it most efficiently. For the first phase, the solution was rather simple. We made a nearest frontier algorithm to direct the robot to explore its surroundings. Then in the second phase, we had to experiment a little more. We first started with a basic DFS plus backtracking algorithm, which eventually evolved into a dynamic A-star algorithm, such that the next go was calculated dynamically after the previous go had been calculated.
Here, we visualize what our Jetson Aura Nano sees with the LiDAR. Utilizing out-of-the-box solutions built into ROS2, we were able to successfully display a real-time updating map, utilizing the input scans from the LiDAR in the SLAM Toolbox package. Here, we utilized the RF20 LiDAR odometry package for odometry data to position our robot within the map, and then we utilized Navigation 2 to generate a cost map on top of the occupancy map generated using our odometry and scan data. As you can see here, utilizing our frontier-based algorithm, our robot navigates around the map to better map out the room. The room is then easily visualized in RViz2. Then, utilizing Nav2, we are then able to set goes, telling our robot where the next go is, through providing a stream of command velocity vectors.
Our robot's software architecture relies heavily on ROS2 Humble, which provides the modularity and scalability needed for a project like MapSuite. Here's a brief overview of our ROS2 nodes and setup. We chose ROS2 Humble for its enhanced real-time capabilities, improved middleware support, and compatibility with the state-of-the-art tools like Nav2 and SLAM Toolbox. It also allowed us to build a highly modular system where each subsystem operates as its own node, making debugging and integration more manageable. The SLAM Toolbox node handles real-time mapping and localization. Using the LiDAR data from our RP LiDAR A1NA, it generates a detailed map of the environment and tracks the robot's position within that map. This node is critical for autonomous navigation, enabling precise movement and coverage. We use the RF20 laser odometry node to provide odometry data to the robot without relying on wheel encoders. This laser-based approach ensures accuracy even on slippery or uneven surfaces where traditional odometry might fail. The data is published to the ODOM topic, which is then consumed by other nodes in the system. The robot control node runs on the NVIDIA Jetson Aura Nano and interfaces with the Arduino Uno over serial communication. It includes a custom PID controller and power adjustment logic to ensure smooth motor operations. The node processes navigation commands and converts them into precise motor control signals, which are sent to the Arduino for execution. Nav2 is responsible for path planning and autonomous navigation. Our bring-up file configures the navigation stack, integrating the map, odometry, and robot control layers. This ensures the robot can dynamically plan and adjust its path in real time. To assist with visualization and debugging, we created a URDF model of the robot, including its motor dynamics. This allows us to simulate the robot's movement in RViz2, providing a clear visual representation of how the robot responds to navigation commands. Together, these ROS2 nodes form a robust and modular system. This architecture not only meets the demands of our project, but also sets a strong foundation for future enhancements and scalability.